No. We will wait, ma.
Now we can start.
Yes, sir. Initiated, sir. Recording initiated. 1 minute, sir. Vishwa, you can start, ma.
Good evening to one and all present here. I welcome you all for today's webinar topic, Trends in Semiconductor Industry. Mr. H.R. Mohan, Chair Events IEEE CS Madras, to deliver the welcome address and introduction to speaker. I welcome you, sir.
Greetings, good evening and to one and all. On behalf of the organizing units, IEEE Circuits and Systems Society, IEEE Computer Society, CSI Chennai, and ACM Chennai, I extend a warm welcome to our today's speaker, Mr. Venkat Krishnan, the members and my colleagues from the organizing units, and the participants who have joined for this presentation through the Google Meet meeting link, and those watching the session through YouTube streaming. Semiconductor industry is hot due to hardware requirements coming out of the demand for the artificial intelligence models and a rapid development. In addition to AI, other market segments such as IoT, automotive are also positively impacting the industry. In our today's presentation, the speaker will talk about industry trends and requirements of semiconductor technology in different market segments. He will also provide an overview of engineering trends in semiconductor industry, including the role of intellectual property, development methodologies, etc. Now let me have the pleasure of introducing the speaker. Mr. Venkat Krishnan is passionate engineering executive in the semiconductor industry with focus on developing digital circuit for IPs, system on chips, and ASICs. He has overall 30 plus years of electronic and communication engineering industry experience, of which over 10 years of experience at executive level in Synopsys and Infineon technologies. During this tenure, he has developed ultra-low power digital implementation for Bluetooth subsystem and ASIC, multiple generations of USB IPs, multiple wireless system designs, including OFDM based UWB, IP, IPs for connectivity applications such as SDMMC, CDMA based mobile systems, and satellite communication systems. She has also built engineering organizations across diverse countries to develop complex and cutting edge technology products. Mr. Venkat Krishnan holds a master's in science and data analytics from Georgia Institute of Technology with focus on business analytics. He loves statistics and its relationship to signal processing. Later, this love led him to artificial intelligence. He has written several papers in IEEE publication and holds a joint US patent on DFT implementation. With this brief intro, let me now request Mr. Venkat Krishnan to enlighten our participants on the trends in semiconductor. Over to Mr. Venkat.
Thank you, Mr. Mohan, for the kind introduction. And good morning and good evening to everyone. Thank you for joining on your Friday evening. I'm very happy to be here talking about my favorite topic, that is semiconductor industry. Let me share my slides. All right. So semiconductor industry and its trends, it's a very broad topic. What I'll do is I will focus on some of the specific market segments and what are the driving factors from this market segment driving the semiconductor industry, and then focus on the engineering aspects. I also fine-tune this session a bit, seeing the interest and questions from early questions about engineering careers and related to semiconductor industry. So I will focus on them. This is the high-level agenda. We will start with the semiconductor industry overview, more of an historical view, and then jump into industry trends. As I mentioned, the key trends that we'll focus on today are the AI. Of course, artificial intelligence is everywhere now. Automotive, and then I will talk about Internet of Things. Finally, we'll also look at the semiconductor IPs, which are kind of reinvigorating the semiconductor industry through innovation by providing readily available design solutions to ASIC developers. And then I will end with some tips on engineering careers. What are some of the hot trends that we see before we conclude. Let me start with an statement saying that we are truly in an exciting time in semiconductor industry. I'm saying this specifically from the recent announcement from all the major countries in the world, including India, uh, announcing that it's going to invest into semiconductor industry. I know India has announced $15 billion, US has $50 billion. This is partly driven by geopolitics, partly driven by security, but nevertheless, it's going to benefit the semiconductor industry. The focus is on manufacturing, but anything done on the manufacturing, it's going to kind of reflect back or percolate into other other parts of semiconductor industry to like design starts or startups. On the right side, I've shown some of the investments that are happening in India, specifically the projects that are coming up. This is a bit of old slide. There could be some changes with respect to this as things are changing dynamically. Some projects got removed, some projects are getting added, but nevertheless, the bottom line is it is a realistic action that is taking place across the country. So it's truly an exciting time in India and also in the US as well for the semiconductor industry. Talking about history, let me start with my own story. Back in 1990s, I was a satellite communication receiver developer, and for the receiver that I designed, it's a mixed signal receiver. That means part of it is analog and part of it is in digital. The analog part was built using a set of discrete components, and the digital part was built using TI, DSP processor, ASIC, and FPGA. And there were ADC and DAC blocks that were added, all of them assembled in one PCB. And the PCB itself became around 1 foot, that is 12 inches by 6 inches size. It was unwieldy, and we had to put it in a box. It had its own stability issues. So all these were arising due to the discrete components. This was way back in 90s. And 20 years fast forward, I was then working on a chip similar to the satellite communication receiver, receiving a 2.4 gigahertz signal. But this time, all the analog and digital, all of them circuits were put into a 20 mm squared semiconductor chip. Nothing else was required except for connecting to the antenna, of course. But the bottom line is the miniaturization has tremendously impacted over these years in the semiconductor industry. This in turn impacted all other industries as well. So no more discrete; it's all integrated chips that's driving the overall electronics industry. And even more bit of history, I'll quickly walk through this. So the first transistor was invented in late 1940s, and in late 1950s, IC got introduced, and then started the exponential growth over these years. And we are in 2020s. We could see NVIDIA Blackwell chip. I wouldn't call it chip; it's a product which has got over 200 billion transistors on it. And we are talking about a 4 nanometer process. And way back in late 90s, again, when I started, it was 180 nanometers. So it is the technology node is progressing day by day. And talking about the technology node, we cannot avoid talking about Moore's law. So Moore's law states that the number of transistors doubles every 2 years. Okay, so on the left side, you see the number of transistors. On the x-axis is the timeline. So from 1970 all the way up to 2021, this is roughly the amount of transistors in one chip is roughly following the Moore's law. People always say that it's going to break it sometime, but it is not fully broken yet. So it is still valid. And this complexity on a chip, it keeps growing as NVIDIA chip has shown in the recent times. And this growth is, of course, impacting semiconductor industry, but it is also an impact on all other segments of industries. Let me talk about it a bit more. So talking about the applications and segments, um, I have tried to color code it a bit. The consumer connectivity, computing, and AI, all of them typically demand on performance, that is throughput, higher and higher throughput, and higher and higher processing in terms of computing is being demanded. Whereas on the IoT, which is green colored shown here, it is driven primarily from miniaturization point of view and also from low power point of view. A good example is an IC sitting on a smartwatch. And the other set of segments is the industrial, automotive, and all others, right? Industrial is primarily automation and robotics. And automotive is autonomous driving, infotainment. Infotainment means the person sitting inside the car getting to hear or seeing different media within the car, and of course electrification, moving away from internal combustion based car to electrified cars. So all these segments are getting benefited by the semiconductor industry. I'm going to focus on three key segments in this set of segments, and they are AI. I'm going to spend more time on AI compared to other two, and other two are automotive and IoT. Okay. Just one other comment on the AI. It's primarily getting driven by the demand on servers, like what we have seen, set of GPUs to process all the AI trainings and AI algorithms, and storage systems. A huge amount of memories are required to handle the data moving across all these processes. So that's the demand on all these semiconductor chips. Let's start with the AI. I put an arrow mark on both the ways. AI is creating huge demand on semiconductors innovation. A lot of chips are coming out to meet that demand. Another aspect is like any other industry, semiconductor industry is itself getting impacted by AI. What I mean by that is the AI based workflows are impacting how engineering is happening for developing the semiconductors. So we'll talk about that also in both the aspects in next few slides. And of course, at the heart of AI innovation lies the fundamental enabler that is semiconductors. That can be seen from how NVIDIA has grown tremendously over last few years because of the AI boom. And NVIDIA is, of course, a semiconductor company. So I talked about this in a bit. The market growth is currently primarily being driven by AI. If a company, if you are associated with AI, then you are going to have a demand. Okay, and the demand comes from 2 or 3 driving factors. New AI algorithms and models are coming into play, and that means they require more powerful and efficient hardware for training purposes, for example. But also there is now an increasing demand and innovation requirement on the inference side. When we say inference, once the model is trained and it is put it onto the real-time usage, how the example is pattern recognition that happens and an inference is made, and that requires sometimes local hardware or a local MCU to process it, and that's what I'm calling it as an edge AI here. And this local devices nowadays becoming more and more smarter and with the AI powered features, and that in turn again creates innovation and requirements. So one aspect is innovation in the all the data centers, and the second aspect is all the devices that are sitting on the edge AI. So all these are creating the demand for newer chips, and even to compete with NVIDIA, I see a lot of startups doing their own GPUs, processors, either for the data centers or for the edge AI. I'm going to dwell some more in details onto the requirements on the hardware. Of course, on the top of the list is the requirement of GPUs, right? So we can see that NVIDIA's Blackwell chips itself keep becoming more and more powerful and more complex in supporting the AI algorithms. And I talked about the edge AI and local inference. These require different approach. Of course, the low power is still a requirement there for a device sitting on the edge AI. So that requires another level of innovation compared to the GPUs or compared to the traditional GPUs. They also require GPUs, but sometimes they may not be as complex. Cannot be as complex as the ones that are sitting in the data centers. And specialized AI chips and chiplets are coming into play now. Chiplets is like in the case of NVIDIA Blackwell. The complexity is so huge that you cannot afford to make all of them in one single chip. So you put the design in multi-die and connect them to a high-speed connectivity, either using an UCIe, that is an universal interconnect express protocol, or it also requires a lot of DRAMs, 3D stacked DRAM, so that the data can be transferred across the processors and stored and retrieved quickly. So that's also driving the innovation on the memory side. I mean, AI is driving the memory innovation on the memory side. And lastly, especially the hardware sitting on the data center requires robustness or a reliability, high reliability. We cannot afford them to keep failing. One way to address is redundancy, keep building redundancy in these data centers, or keep improving how the reliability of the devices themselves. And the other thing that keeps driving or improving is the security in the data centers. So that's the other aspect, like the encryption or how to transfer data in a secure manner. All of them are also driving the innovation. I wanted to also talk about a bit more futuristic. What are the advancements that are seen? Of course, the AI specific chip, you will see more and more coming into market, and people are trying to design in more optimized tensor processing units. And TPU is the is a basic unit designed to accelerate machine learning tasks, and they are built together to improve the processing efficiency for AI workloads. So that's where a lot of advancements are happening. There is also an advancement that is happening around how the neural network is built and how the neuromorphic chips mimic the neural structure of the human brain itself. That's again coming to optimizing processing of complex AI tasks. This consumes a lot of power, and that is becoming an increasing challenge. That's what making people to look at other ways to do the computing. Quantum computing is again, it's there for a long time, but it is becoming more prominent now. If anybody is doing research, this is one good space to look at. The security and cryptography is also being relooked with respect to in the advent of quantum computing. It's called PQC, the post-quantum computing. How post-quantum cryptography, how the security can be improved with the quantum computing happening in parallel in the industry. And lastly, photonics also becoming hotter. Even companies like TSMC or Global Foundries, they're all looking at how to exploit photonics to improve the connectivity in the data centers or connectivity within the chip itself. So these are the advancements that are seen, driven from AI, but happening at the level of at the chip level. So far we talked about how AI is demanding and what are the advancements or the trends that are seen in the in the semiconductor chip. Now we'll look at how AI is enabling the semiconductor development from engineering point of view. This chart I took from McKinsey recently. It got published. This shows that amount of or the cost involved in doing or in developing a chip. So on the x-axis is basically the technology node size. It starts all the way from 65 nanometer and to the latest 5 nanometer, 4 nanometer. On the y-axis, we have the cost involved in developing a chip. So earlier at the 65 nanometer, it was around 30 million to develop $30 million to develop a chip. Now with the 5 nanometers, it is close to $550 million to develop one chip, and this almost getting doubled, right, with respect to 7 nanometers. So the cost of development essentially is increasing, and the effort to develop is also increasing. It's not just the manufacturing cost we are talking about. The development cost itself is high as the node size keeps decreasing, and it is going to go further down unless some photonic is going to dominate how the chips get designed. This basically indicates that there is a need to for us to do differently the development of ASIC. So that is where AI is being looked at. Like any other industry, AI is impacting how things are done in semiconductor chip development. When you talk about ASIC flow, we'll always talk about front end and back end. Front end is where the design spec and RTL coding, if you consider it's a digital design, and synthesis up to synthesis happens, and back end is where the floor planning, placement, and routing happens. Finally, product gets released with the documentation. In all these phases, all these steps of ASIC design flow, the EDA tools are getting used, and they are becoming smarter with assistive agents. For example, when I designed the chip, I used to write the Tickle scripts or Perl scripts to process different outcomes or define the tool flow itself. But nowadays, with the AI assistive agents in place, we don't need to manually write them. You can use the agents to get the Tickle scripts or even Python scripts to be generated and used for different purposes. That's one aspect which is useful for engineers. The other aspect is, of course, the Gen AI. You can be used for creating at least a starting point of a design specification, and then engineers can update them, modify them, package them as needed. The RTL generation is still done manually, in my view. The tool, at least not yet ready, compared to a software engineering, where a C code or a Python code can be easily generated by the AI tool. Here, in the semiconductor, it's not there. This is primarily because that the models are not ready trained on RTL. So manual method is still getting used. On the verification side, there is a very good level of um, uh, assistance provided by the AI. So you can generate for a formal verification, for example, you can generate the constraints and checkers very quickly using AI, and you can set up a formal verification moment in no time. On the functional simulation, when given sometime probably 8-9 years back, I have used the ML method to process huge regressions that we used to run, and the outcome of simulation run had to be processed with the AI tool to quickly categorize the failures and to debug the failure. AI assistance could be taken, and it could increase the productivity. So functional simulation and even in generation of test cases, analysis, AI methods can be used, and engineers should be aware of them. Static verification, when I say static verification, I'm talking about, for example, CDC analysis using a static tool. It throws up a lot of noise, and an AI tool can help in navigating them through and quickly, analyzing the results of static verification outcome. So that's again an area where the AI tool or AI is quite beneficial. And then in the back end, the floor planning, placement, and routing are becoming more productive with the AI assistance in place, because it can give uh, when there is a huge volume to be handled, these tools can definitely help. And lastly, the product documentation can be done by either by the engineer or the marketing quickly with the Gen AI being used. So almost all the part of ASIC flow is kind of getting impacted by AI, and as engineers, we all need to be aware and use them as needed. So that's about AI segment, how AI creating demand on semiconductor industry, and also how AI is helping improving the productivity in developing the chips. Let's talk about the automotive segments. Primarily, when we talk about automotive, it is automation. Automation means like height of automation is the self-driving car and EV electric vehicles that are coming into play nowadays. And semiconductors form the bedrock of innovation there. Bit of history, how the electronics are getting into the car. It's all, I mean, the automotive industry is, it's not easy to change. It takes time to introduce any change there. It started in early 90s with the basic electronics going to car. This electronics were used to control the fuel injection and improve the efficiency of engine that was operating. Simple MCUs as used along with some sensors. And in 2000s, the complexity started growing. More MCUs and control units were getting added into the car. That primary purpose was infotainment, the climate control, and some sensor networks for diagnosis. For example, tire pressure monitoring was one example where the sensor and electronics and semiconductors were put in place. And in 2010s, it's further grew. Advanced driver assistance systems, put it simply as ADAS, came into play. A good example is when we are driving a car in one lane, when there is another car coming on the next lane, the sensor will detect and let the driver know that no, don't change the lane now. So that is one good example of ADAS, and that was made possible by a set of semiconductor chips along with sensors sitting in the car. And parking assistance became quite popular during this time. That led to 2020s or late 2010s, where almost we call it computer on wheels are getting built now. There are over 100 MCUs and level 2, level 3 autonomy features got built in. Then high resolution display sitting in the car in the cockpit now. And there is an advanced communication and battery management system, over the air updates for the car. All are happening as we speak. So that is a tremendous change that the automotive industry is undergoing, enabled by semiconductors. And this changes are being driven by three key drivers. Electrification, of course, it's on the top of the list. With increasing EVs are coming into play, or close to 30% is what is predicted in the next 5 years. And connectivity for the cars keep becoming complex and increasing. Vehicle-to-vehicle communication or vehicle-to-infrastructure communication, and autonomous drive from different ADAS capability. I mean, from ADAS to full autonomous is being built into different cars. And talking about the complexity, currently the 40% of bill of material for the new cars is electronics, and it's all, when we say electronics, all about semiconductor chips. Over 1,000 to 10,000 semiconductors are going into the EVs nowadays. And I talked about the functions bit already. The driver assist and ADAS are the ones primarily getting benefited by the semiconductors. Battery management system is a very important aspect. How the battery is managed, how to when to charge, so that the efficiency of usage keeps doing better, and range of car becomes better. That's what being done with the BMS, complex BMS in place. Connectivity keeps improving, and GPS are getting built into the car. Wi-Fi, Bluetooth combo chips are sitting in the car. Ethernet is connecting all the components in the vehicle, and security is also getting added to the chips. And lastly, the safety is another functionality getting benefited by the semiconductor chips. Whether we talked about it, sensors detecting nearby vehicles and avoiding collision, or deploying airbags. All these are controlled by semiconductors now. That's the another function that's getting benefited by semiconductors. In terms of innovation, enhancing performance of the car, it keeps improving. How the whether to coming with the range of the electric cars, or even in the internal combustion engine, the mileage is also getting improved because of the improved electronics. And I talked about already the safety and automation improvements are getting improved with more and more innovation. For the EV technology, power semiconductors are playing a major role. The gallium nitride technology is being heavily used on the charging side, right? The car is one, but the charging network require high power electronics, and we are now looking at other than silicon and silicon germanium nodes, like processing nodes like gallium nitride are being looked at. And I talked about the battery technology and BMS also getting innovated to improve how the cars getting charged, and how they can increase the range of for the cars. So that's about the automotive industry. Primarily electrification and autonomous driving and safety are the ones which are driving the semiconductor in cars. That brings us to the third segment, that is IoT. Compared to AI and automotive, IoT is driven by a completely different set of requirements. It's about low power and miniaturization or small area. And IoT is booming. What I mean by that is every device is now getting translated into smart device, right? By adding connectivity or yeah, an MCU to that. And so that is also evident from the data in it, the number of devices getting connected, or number of IoT devices keeps increasing every year. And 2024, close to 19 billion devices were there in the market. And this is all these devices require low power consumption, compact size, and connectivity in data processing. For example, your device sitting in an industry control needs to connect to a central processing unit without manually accessing it, and that is possible with making that remote unit smarter with connectivity attached to it. Connectivity, when you say, it could be a Wi-Fi or even a Bluetooth or a UWB. And there are some sub-segments. IoT is a massively huge term. There are anything is possible to be connected, but we are trying to segment it further. Smart home, like smart lock, when you don't need to use a manual key, but use a smart key to open your home. Smart doorbell, appliances, lighting is one place where it's becoming more and more innovation coming into play there with the Wi-Fi connected to it. Healthcare, we all know that many people are now wearing the glucose monitoring patch and connecting it to mobile. Hearing aid is also becoming smarter and better. Wearables like smartwatch getting benefited by the semiconductors. Then industrial automation and monitoring is another place where the semiconductors play a huge role. We touched upon it briefly. I just wanted to mention a couple of things here. The trends in the IoT. IoT is also about cost. We cannot make a very complex, huge, with a high cost integrated chip for an IoT. It has to be always cost is a factor there. So compared to say AI or AI, here it's a higher technology node being used. For example, in the current trend, 22 nanometer or 16 nanometer is typically used compared to 7 nanometer or 5 nanometer, 4 nanometer in the AI chips. So the requirement is different here, and the trend of integration or technology node is also different in the IoT segment. But there also it keeps improving because the demand is there on the low power and low area. We want to put more logic into smaller area. That is still a requirement even in IoT also. And the growth of IoT is also aided by AI. I talked about it in the AI segment. The device that is sitting in the remote is also being looked at to add AI feature to it, so that, for example, any pattern recognition or pattern detection can be done with the less latency instead of going back to cloud and processing there. So again, edge AI and is benefiting the growth of IoT. So new opportunities are being created here, and a lot of innovation again happens in this space. The smarter devices, they need to be connected. I talked about it. So it requires first a set of MCUs or at least one MCU in it. That is microcontroller unit. Along with that, it needs to be connected to a phone or other systems through Wi-Fi, Bluetooth. The real-time location service, that is called RTL, is also becoming quite popular now, and either a Bluetooth technology-based or channel sounding feature, or an UWB-based or ranging feature, or getting implemented to do the real-time location services. So that's the another trend that we see in IoT. All right. So that's the coverage about three market segments: AI, automotive, and IoT. Let's talk about an IP. When I say IP, it's basically intellectual property, in a broader sense, but it is, to be more correct, it should be called semiconductor IP, SIP. And these are all semiconductor design blocks, which are made readily available and to be used by the ASIC vendors or ASIC developers. The IPs are primarily getting driven by the standard specifications that are evolving. Good examples of standard specifications are USB and MIPI. This standards, they help in making the different devices interoperable to each other, so that in a good ecosystem could be built beyond the competition that keeps driving the innovation. And IPs are built to meet these standards or to be compliant to the standards. And that way, someone like, say, you are building an AI chip, and you'll be focusing on the how to build an efficient chip processing the AI algorithms. But it requires connectivity, and you can use the IPs from a third-party vendor and put them across along with the processors to build a chip. So that is where the IPs help in driving the innovation, and the new products are getting done more quickly compared to earlier. Earlier, if you want to build an ASIC, you would be writing everything for peripherals also, but that's no longer the case. You can quickly use and readily available IP and build your chip, and that also more cost effective. You don't need to spend a lot of time, and it also brings the time to market for the chips down, so that you can quickly get your ASIC out. So that's the primary advantage of IPs, and a lot of startups and companies are increasingly becoming involved in developing IPs and providing to ASIC vendors. In terms of market trend, this is the data taken from IP Nest. It, as you can see from over last 5-6 years, it keeps the overall market size is increasing for IPs. In 2024, it was close to 9 billion, and it is projected to increase down the timeline too. And there are major players. ARM, for example, they provide the processor IPs. Synopsys is big time into providing all kinds of peripheral IPs to ASIC developers, and they are the dominant player there. The other companies like Cadence, AlphaWave, VeriSilicon, they're also in this space. Some of the popular IP portfolios, I segmented them different market segments. Connectivity is of course very popular. PC Express, USB, I3C, these are the good examples of IPs that are prominently used by ASIC vendors. Memory controllers like SDMMC controller or DDR are also very, very popular. Processors, we talked about ARM processor. RISC-V is becoming quite popular because of its open ISA structure. And if someone wants to jump into IP development, I would suggest to look at RISC-V definitely, and then make an IP out of it and give it to customers for different applications. ASIC infrastructure like power management is becoming more and more complex. Providing IP for it is also in becoming demanding segment now. if you want to also provide connectivity in terms of wireless connectivity to customers, you can give that using Wi-Fi subsystem or Wi-Fi IP, Bluetooth IP, and data path IPs are also available. A lot of them: JPEG, MPEG, voice codecs, channel codecs, like Viterbi decoder, and security crypto engines. AES also quite popular in terms of IPs because of standardized algorithms that are there. Let me talk about quickly the some of the tips. It's about if you are trying to decide which IP to develop, you need to strike a balance between the complexity and reusability. What I mean by that is, if you make the IP too complex, then you will end up customizing it for customers. It will be very hard to make it reusable. But if you make it too small, then it loses the value. Customers can write their own IP. They don't need the IP from you. So it has to be balanced between complexity and reusability. And keep the interfaces standard. What I mean by that is, if you're developing IP on one side, you build the AHB bus, and other side you build for example, two-wire interface like SPI, so that it is easily usable or easily integratable by the ASIC vendors, and ensure that the specification is public and available, so that again the integration is can be done quickly by the vendors. Try to give the entire subsystem, meaning don't give a one piece of IP, but give the entire software, hardware, and firmware. A soft IP, hard IP, and firmware. Hard IP, when I say the physical layer requires an analog components to be present, and that means they need to be technology specific, technology node specific. That's what I mean by hard IP there. So soft IP, hard IP, and firmware can be given as a one full subsystem solution to customers. One important aspect of IP is the quality, because the customers will assume that it is already fully verified. So you want to make it a high quality one, verify it, fully validate it before you release it to customers. And keep the IPs warm and alive. It means that as the standard spec evolves, you need to keep updating your design so that it is full of features and readily usable by customers for latest applications. And if you want to become an engineer in IP space, you will typically expected to be strong on interface protocols. Learn about AHB, learn about PCI Express, and learn about, for example, UCIe. I talked about the protocol which is between multiple dies, multi-die interfaces. So be aware of them, these protocols, and that will help in becoming a successful IP engineer. Before I conclude, I want to touch upon this topic because, based on the preliminary questions that I see, people are asking what can be a good career. So, semiconductor industry offers a lot of space for engineers to play, starting with the electronic design automation, that is EDA tools and flows and methodologies itself. So, for example, you want to become a verification engineer, be aware of how to do formal verification, how to write SV assertions, system verilog code, how to write them. UVM is another methodology that you need to be aware of, and then learn about how the synthesis happens, how the implementation flow happens. In the case of these are all the flows that you need to be aware of. And if you want to start becoming ASIC engineer, understand what is front end, back end, you can become a front end engineer or a back end engineer. All of them have their own challenges, and be aware of depending on your interest. Be aware of the challenges involved in each of these spaces. And you can become a digital or analog engineer, an RF engineer. All of them have their own challenges and requirements. Design, you can become a design engineer or verification engineer. For every IP or ASIC design, the design part is only a 30% of effort. The verification is where the majority effort happens. 70 to 80% effort is verification. So that's where the demands are higher. And it's also equally challenging role to play compared. You don't want to just say that, okay, I want to become only design. Verification is also a good space to look at. And IPs can be an implementation IP where RTL is written or a SPICE model is written, but it can be a verification IP also where reusable test benches and reusable bug functional models can be done and given to customers. Interconnectivity, I talked about it. It can be an intra-chip like a bus interface or an intra-chip or intra-chiplet. So all these are protocols driven connectivity requirements. You need to be aware of them if you want to become a plain IP space. FPGA and emulation is also another domain which is quite demanding. Keeps every industry, every semiconductor, they need to do this FPGA validation before they tape out the chip. So design and validation and emulation, all of them are requiring engineering talent. If you look at it functionally, you can become a processor designer, a processor architect. High performance computing is driving the innovation, and a lot of designs are happening around this space. I talked about the high speed memory requirements from AI. Embedded systems for IoT is also in a good space to look at. You need to be aware of connectivity protocols, low power design, and power electronics also an important space to consider. And DSP blocks like Viterbi decoder or modems are also keep improving. That's where one can become an focus on the DSP designs, or you can become an analog engineer, either develop a physical layer or RF design. And roles, you can be an R&D engineer, or you can also become an application engineer. It requires an understanding of the systems and provide guidance to customers on how they can use ASIC or how they can use IP. You can also become a product engineer, collecting the requirements from customer and defining the requirements of product to the engineering teams. Or you can become a program manager, because ASIC development is a complex program to be managed, and being aware of the methodology cleanly can help a good program manager to be successful. So these are all the variety of roles and possible careers one can take in the semiconductor industry. That brings me to the final slide. Key takeaways on the advancements and advancements in technology and the market demands are driving the semiconductor industry. As I mentioned, AI, automotive, and IoT. There is also other segments like 6G and satellite communication is also coming back with their own requirements. And a lot of investments are happening, as I mentioned, by countries and also by not only by governments but also by the private players like Intel or Nvidia. So all this will benefit the semiconductor industry, and it is an exciting time to be there. I talked about the key segments and driving factors: AI, automotive, and IoT. And developing IP is also a good way to drive this innovation or ride this innovation. And lastly, as an engineer, changes are happening around all of us because of AI. So be adaptive and navigate the future with more and more learning. That's the way to be successful. One is handling the complexity, but at the same time, it is important to be firm-footed on the concepts methodology. What I mean by that, and it is easy to write a system Verilog code, but you need to understand how the Verilog code is getting translated into actual digital design. So you need to be clear about CDC concepts, the clock domain crossings, or about how to meet the timing, how to write an FSM, right? Finite state machine. So all these are very important still. We cannot ignore them. So be thorough on your concepts and be aware of methodologies that will make you successful in semiconductor industry. With that, I have a few references quoted here where I, when I did the research for this presentation, I took the material from there, I quoted them. And there are excellent courses in Coursera and Udemy one can consider if they want to learn. I'm a big fan of Coursera. I myself go through a lot of courses there. If you do a search on digital design, for example, you get multiple courses. You want to understand, okay, I want to become better in digital design, then there are courses, you look at them. So it depends on what is your interest and depends on where you see that you need to pick up. So you can do your search and get the course out and clear them. So with that, let me say thank you again for your time listening to me. It's truly an exciting time. I'm very, very happy to talk about the trends and hope I could give some glimpse of what is in store for you if you want to take up a career in semiconductor industry. Thank you. I'm open for questions. I'd be happy to answer them. In case it's beyond me, I will take in action and definitely get back to you.
Thank you, sir. The presentation is very nice, sir. Yes, madam, please. Thank you, sir. The presentation is very nice, sir. I hope all the participants gained more knowledge on the semiconductor industry. So we have received some of the questions from our participants. Let me ask one by one, sir. The first one is, what skills or interdisciplinary knowledge will be most valuable for students aspiring to join the semiconductor industry in the next decade?
Yeah, I think I kind of answered that question through this entire session, right? I would say in the immediately the demands are coming from AI. So being aware of what are those demands, like understanding what is a RISC-V processor is a one example I could give. So understand how these processors are getting tuned or configured for processing AI algorithms. The HPC, high performance computing, is also another place to look at. That includes all the connectivity, how the different processors are getting connected to form a supercomputer, right? So these are the aspects to look at, and also I talked about the how the AI is assisting engineers in improving their productivity, right? When you're using a tool, you can use the AI to give a script quickly. You don't need to write it manually. So being aware of them will help you become better. When I say better, you become faster in getting your solutions, and be aware of the trends in IPs. So that also it's a good place to look at. So that's my answer. So be aware of the system requirement. When I say system, I mean AI system or automotive system or IoT, and then how it translates to semiconductor is a good place to start with.
Thank you, sir. Next one is, for educational purposes, what are the available stimulus tools used in semiconductor applications? Also, which algorithms are commonly used in IP engineering?
Yeah, again, I let me talk about the second part, IPs, right? So I talked about it. These are all driven primarily by the evolution of standards, right? For example, MIPI is a is an organization which is providing standards for mobile platform. Okay, and they talk about how the camera is getting interfaced, and the interface is very cleanly specified. So being aware of this protocol and interface, how it works, are the key to key to the IP's enablement. And the tools, of course, simulation tool, right? If you're writing a system Verilog code and you want to simulate and see whether it is working as expected, right? So you need to have the simulation tools and also your synthesis tool to translate your digital design into your gate level netlist or implementation finally. There are open source tools that are available for simulation nowadays. So you can if you are constrained by the license unavailability, you can consider the open source tools and start with them. And if you do a Google search, you will usually get the open source tools. I don't have it readily in hand. I can check up and share it later if required. That is one place to start with. Anything that you are writing, you want to simulate and ensure that it is working as expected. So that's where you need the simulation tool to start with. And there are synthesis tools that are there too, like a design compiler. For students, there are low-cost versions available, or if you are associated with the university, definitely you can access those tools in the university. I'm through this. I'm also want to mention that all these EDA tool vendors, like example Synopsys, Cadence, or Siemens, Mentor Graphics, all of them have partnership with universities providing the tool. So at least all the popular universities have these tools available to them. When again, right, simulation tool or synthesis tool, or static verification for all of them, right? And this is where the investment is required, and the initiative has to be taken by the institutes and universities to go to the industry and talk to them and see how the tools can be made available to the students. So go to, if you are associated to the university, please go back to university and see what tools they have for semiconductor chip implementation, whether it can be simulation or synthesis, or even what IPs are being available for access. I would say you put them into an FPGA flow. If your lab may be having an FPGA system in place, you can put it onto that and actually probe using oscilloscope and see how your circuit is working. So these are all very quickly possible nowadays. So I would encourage you to access the tools and write a small code. It's very easy to write nowadays, with all the internet resources that are available to you, and then try it out on actual hardware.
Thank you, sir. So next one is why India has failed as a provider of technologies. We have become a pure consumer state. Is it a lack of having an R&D culture? Will it change in the near future? This is next question.
It's a very good question. Let me try. It's a complex answer to it. The any technology, right, advancement requires a few things. One is the talent, and talent is engineering talent. But yeah, that's what I primarily mean, and that in turn also means that you have good set of universities to be available, or academic institutes to be available. So talent is one aspect, and second is the investment and also the ecosystem to groom the technology. When I say investment, it typically needs to be happening from both the government and also from the private players too. So I wouldn't say India is failed. India is lagging, right? It is coming up or picking up. In terms of talent, there is no dearth of talent. We all know that. We have all kinds of engineering done. If anybody wants to do your ASIC design, everybody will first look at India as a place to do that design work. Okay, the key problem that we have is on the investment side so far, right? We didn't we meaning I'm talking about the either from as a government or from even from the private players. The investment did not happen that heavily. Our focus was not there on semiconductor. It is coming up now, as I mentioned in my first slide. So it's a good thing. It should help. So the talent is already there. The R&D culture is there. In fact, the for companies like Qualcomm and TI, India is the place where actually the ASIC design happens. So it's not the design is happening in US. So talent is not a problem. R&D culture is not a problem. It's the investment. If for example, a semiconductor manufacturing plant is there or plants are there, that would encourage more and more designs to happen locally, and it will bring down the cost. If you look at in parallel to China, they started much earlier. They have the SMIC already fully running. They serve the local market, and the government subsidy is there for all the players. Huawei and HiSilicon got hugely benefited from the government subsidy or government investment, right? So it requires some government stimulus or push, unfortunately, and that's happening now. And I'm optimistic and positive that things will become better in India also, and it will become a major player in semiconductor industry.
Thank you, sir. Next one is, what are the specific skills to be developed by students in particular field of semiconductor industry? Certification course that can be chosen will respect to which domain or subdomains?
Yeah, again, right. I knew this kind of question will be lingering in students' minds. That's why I talked about it a bit towards the end of my session. I touched upon few things like if you want to become a verification engineer, right? Be clear about UVM methodology, right? You know how to write in system Verilog code, how to work on or develop an UVM environment, right? If you are on the design side, again, be clear on concepts, design concepts, how to write in RTL, how it translates to implementation, how to write in FSM. And if you are if you want to become an RF or analog engineer, be aware of SPICE models, how to write analog SPICE model, how to verify it. So if you look at it, there is a statement I keep making: if you want to become, right? So there is a lot of scope, as I mentioned, and it has to start with what you want to do, right? What you want to become, and be passionate about it, and focus on it, and develop the skills from all these courses that are there, right? Like Coursera, I talked about. I don't want to actually suggest a very specific course for, okay, everybody should take this, right? Then it doesn't work that way, unfortunately. And I know that, as a student, you want to look for a specific and you go and, pursue that, but everybody will not be having the same inclination. For example, one person would never like working on analog, right? They don't want to deal with op-amps. They don't want to deal with transistor level. They want to deal at the RTL, or some other will be wanting to become verification. So it also depends on what you want to become. So I talked about all the different spaces that are possible. You choose one and go through it. So that's my suggestion. And all of them are having their own requirements in the industry. And I would say if you're open to everything, I would say verification is a space you want to look at because the demands are higher there. A lot of companies are playing, and as I mentioned, when you say demand is higher, 70% of the effort is verification. That means more and more engineers are required there. So you want to consider that. That would be my if you are looking for specific anything advice, that would be my advice.
Thank you, sir. Next one is what should be the focus areas of research for semiconductor industry in India, sir?
Research. Yeah, I touched upon this too. So of course, AI. I talked about each of the segments. I talked about where the advancements are happening, and that's where the research can be looked at. Like in the case of AI, the down the stream, photonics and quantum computing, and related topics like the how to do the cryptography in quantum computing in place, or they're all good areas to look at. And then when I talked about automotive, the power electronics, how to have better batteries, how to build a very high power charging network without less cost. That is what is driving the automotive, so can be a good research topic. And then on the IoT is how to build smaller, more power efficient, but smarter devices. When I say smarter, you want to run an AI algorithm in your camera sitting in the front door, right? But you don't want to consume a lot of power. So that is again a research topic, how the edge AI can be done with least power is a good research topic too. So these are all some of the areas, but the top of the list is something that can enable AI because of the trend. I'm talking about next 3 to 5 years. This is what will be the driving factors.
Thank you, sir. Then next one is, would you provide insight into the current and anticipated future development in the semiconductor industry, as well as the potential employment opportunities it offers?
I'm trying to, the voice got a bit disturbed. I'm trying to understand the question. Would you provide
insights into the current and anticipated future developments in the semiconductor industry, as well as the potential employment opportunities it offers?
Yeah, I think this is the crux of the presentation itself, right? So the trends I talked about, the 3 segments I talked about. In addition to that, there are other segments too, right? The 6G, the 5G and beyond, right? And the cellular communication. But the impact will be more from AI, automotive, and IoT. That's what I see. That the trend I talked about, and how they are translating into requirements on the hardware and how they are getting implemented in chips. There are lot of multiple startups are coming up addressing all these requirements in hardware. I'm very much excited by all this all these trends and how they translate into employment opportunities. And specifically in India, it'll keep driving the talent requirement for sure. That I'm very optimistic about. So this means either developing IPs for newer standard specifications, like even a few days back there was a new specification got released by HBM, high bandwidth memory. So this may be very specific, but even for every one of them, a lot of engineering work is required, and that means there is an opportunity for someone to play a role there, either as a design engineer or verification engineer. And if you are okay with the dealing with analog, I would say that's a very good space to be in. Learn about how the analog design is done on VLSI, how to write a SPICE model, how to simulate it, and also learning about RF circuit, how to design them. For example, how to do a filter design in RF domain, or mixer design. So all of them are good problems, good engineering problems that require solutions by engineers. So these are all also high demand is there. So if you whatever you do, be strong in your concepts and learn about how to use the tools, then you will find the break in your career.
Thank you, sir. Next one is getting into a VLSI company will be worthy and give a good experience instead of embedded or IoT, and also this will have the more of the future development and scope to pursue a career, and how the impacts will be in India in upcoming years, and also what is the difference between VLSI and semiconductor manufacturing industries, and how they will be in future, and how their packages will be in these domains. It's a very big question, sir. Any questions?
Okay, let me try to address each part of it.
Yes, so they asked about VLSI and semiconductor. What's the difference, and also how the future packages will be in the semiconductor industries.
Yeah, understood. So the semiconductor manufacturing is a separate beast by itself. It's a more problem of mechanical engineering than electrical engineering problem. So I won't go put an electronic engineer to go there. Manufacturing involves like you're having a good understanding of material science and good understanding of how the either a doping technology works. So this is a different problem altogether. Whereas when we say VLSI, I talked about the different the ASIC flow, right? Like getting the specification and then writing an RTL and then simulating them, validating them. So this is the design flow we're talking about. So VLSI typically means this flow that we are talking about before going into final manufacturing. So semiconductor manufacturing is just fabricating the chips once all the design is done, right? Say, just to add more information to it, say you want to design an AI chip, okay? So what you do is that, okay, I want to design an AI chip and I'll get the specification for the AI chip. I need to put some GPUs, I need to put some connectivity around it. When I say connectivity, PCI Express or UCI Express, connectivity around it and build your digital chip, all right? That's what I want to do. So you want to start with the specification and then you write an RTL for it or use IPs to put together an integrated system on a chip, and then synthesize it into gates and finally do a place and route, right? Backend you do, and then get what is called the GDS2, right? That's the final netlist which will go into fabrication. So you give it to a company like TSMC, where the actual manufacturing happens, right? So all these steps that I talked about, writing, specification, RTL, etc. These are all happening in another company called fabless company. Like example is Qualcomm is a fabless company. They write get the entire design done and then give it to TSMC for getting the chip manufactured. So the VLSI refers to this the design part, and the manufacturing part is happening in a company like TSMC, right? That is a Taiwan semiconductor manufacturing company. So that these are different aspects. So VLSI defines the flow and the method of creating designs. Hope that explains that. And I talked about the India future. I'm truly positive about it because of the amount of innovation happening in India and engineering talent that is there. And it is if you are in a place like Bangalore or Noida or Chennai, you are in a good space to join the semiconductor industry because of the innovations happening. And that is all engineering wise happening in India. So I'm happy. All this geopolitics also helping India. Because India is more neutral compared to other countries like China. So we should feel feel good about it. So that's on the VLSI manufacturing, and we talked about the. I'm trying to correlate the question. We talked about the how good it is in India, and I also talked about. I also want to talk about the embedded systems. IoT. You asked a question whether to be good in VLSI or IoT. IoT. I think you mean embedded systems. I showed, right, the VLSI is broader. It can go into either AI or automotive or IoT. So VLSI is there everywhere. And embedded systems also an important aspect of VLSI design. Every IoT device will have a processor in it and a firmware to be written for it. And this hardware and firmware will have a heavy interaction with each other. And you need to be a good hardware engineer to write a firmware. So you cannot ignore that, either this or that. That's the difference between an entirely application engineer, software engineer, compared to a firmware engineer. Firmware engineer needs to be well aware of the hardware resources and how to write into memory, how to write into registers, and then write a very well optimized firmware. So my answer to that is challenges are there in both, whether it's in VLSI or in when I say VLSI, whether you are truly a hardware designer or an embedded system developer, both are good spaces. Both have their own demands because IoT is there, proliferating all spaces. Similarly, AI is also having their own requirements. So it is going to be hard for me to choose either this or that. Both are equally good spaces to be there. Okay, and good challenges. If you are in embedded system, you will understand the system better. You will know how for example, how your camera system works and how to write a firmware which will deal with the camera interface and also with the other memories. So both are good spaces to be there.
Thank you, sir. Next one is, what skills will be most in demand for semiconductor professionals in the coming years, sir?
What group will be most important? Can you repeat the question?
What skills will be most in demand for? What skills will be most in demand for semiconductor professionals in the coming years?
Yeah, skills, right? Again, right. There are multiple spaces, and each of them require their own skills. If you are talking about most important, it is, instead of saying most important, I would say, because all of them are important. Without one, you cannot do other. Like if you're doing design, we need the verification engineer. So verification skills are required. So there will be, I would say, the demand-wise, there will be more on verification, right? I mentioned that because of effort-wise, it's a lot more effort to do the verification compared to design. Design will be done in 2 months, whereas verification will happen over 6 months, right? And a lot of engineers are required for verification. So demand will be more there, and it will be a good skill to develop on verification. When you say verification, be clear about how to write a UVM test bench, right? It's a very popular methodology, and that's the methodology used across industry. So be aware of it. And there is also a niche, demand that is there for formal verification engineers. You want to write assertions and checkers and constraints and use it to formally verify a circuit. That's also a good skill to develop. But the demand is not as widespread as the regular traditional simulation-based verification. And RTL design skills using system Verilog is also a good skill to develop. and how to do the FPGA validation is also a good skill that will be there for years to come. And if you are using tools, be aware how to use the AI methods, and be a more productive engineer. That would help. A good skill to develop. And also as the technology nodes keeps advancing, being an analog engineer is also a good skill to develop. But I'm not saying that you need to develop all of them. What I'm saying is that you can pick up one of them and focus on it to become a kind of an expert, right, in that. Because it is hard to be an expert on all of them. I cannot claim myself an analog engineer because I never did analog design myself. So pick up one, either in want to be an RTL designer, verification engineer, analog designer, and focus on it. Okay, so there are ways to courses available to get certified, and you can form a career in them.
Thank you, sir. What is the main difference in between China and India technology?
Yeah. Again, I talked about in a bit. The technology development requires two aspects to simplify everything, right? One is the talent, and the other is the investment and ecosystem part. Talent is there in both the countries, no doubt of it. The talent, when you say the engineering talent and the manpower that is there, the unfortunately or fortunately, China started early, right? They went into this become a big created a big impact in manufacturing center that helped them become better place to adopt technology and create technology, right? In semiconductor industry, I'm talking about. The companies like Huawei is able to have their own solution competing with NVIDIA that cannot be claimed by India. That's because they started the investment into this semiconductor industry much earlier, and that's why they are advanced compared to India in terms of technology proliferation and impact that they have created in the semiconductor industry. The mobile phone that the technology also helped them in becoming successful as a company in impacting technology. That's we never had, right? We never have our own phones, put it bluntly, right? So these are the factors. Essentially, it started there. Probably I wouldn't put a number of years, but probably a decade ahead of us when you say as India, and it takes time. But we should not be comparing too much between countries and go nowhere. But instead, focus on what we can impact now, and just be creative, be innovative, and make an impact. I would say that's what would help our country.
Thank you, sir. That's all, sir. All the questions over, sir. Sir, thank you very much for clearing our participants' doubt in a very grand manner. And also, it's very, very nice, sir. Thank you, sir. Thank you for a detailed explanation also, sir. Thank you.
Thank
Any
you.
other
Thank you,
questions, any of the other questions may rise, sir. From my end over. That's all. Thank you.
I request Dr. A. Akila, Chat, CSI Chennai, to deliver the vote of thanks.
Thank you, Vishwa. First of all, I thank the speaker, Mr. Venkat Krishnan, consultant angel investor, former director Infineon Technologies USA, for his webinar on trends in semiconductor industry. So it was overall very interactive, very nice session. He just explained in terms that everyone can understand. So he just started with saying that the semiconductor industry investment by India is around $15 billion, and he just projected the projects in India that is taken to be taken that is done by semiconductor manufacturing projects. And also he just insisted that IC is driving the electronic industry, and he just specified about the Moore's law, that is the number of transistors in a dense IC doubles roughly every 2 hours. So that is, he was just insisting, and he just told about the the applications, various applications, and on among them he uh, just briefed about IoT and 3 things: IoT and automotive and also AI. So he just mentioned that AI is creating demands of semiconductors, and then he also mentioned about the market growth driven by AI, and he also touched upon the specialized AI chips and chiplets, and he just mentioned neuromorphic chips, about neuromorphic chips, which is mimicking the neural structure of the human brain, and how the semiconductor is making it. And he also uh, discussed about the semiconductor are the bedrock of modern automotive industry. And with semiconductor in IoT, he just mentioned what are all the different things happening with semiconductor and IoT. So he just explained it, and very good interactive Q&A session. So he answered all the questions in detail, and we thanked. And I would like to take this opportunity to thank all the organizing units, IEEE CS, IEEE CAS, and ACM Chennai and CSA Chennai for organizing this webinar. And many of the participants got benefited, and those people who are watching in YouTube also, and who will be watching, will also be feeling this to be very useful. And I take this opportunity to specially thank Mr. H.R. Mohan sir, who is the backbone of this events, chair events IEEE CS Madras. So I thank you, sir. And before ending up, I'm just giving you a short thing of what are all the future webinars we are having. So 11th of June, we are having a webinar on exploring the efficiency and applications of small language models. And on 25th of June, we have a webinar on study in USA, a step-by-step guide to applying to US universities. And on 16th of July, we have a webinar on choice computing and humanized AI. So you can just go to our website, csi-chennai.net, and you can just have a view of all the sessions, and the registration link also will be available. You can just register and attend it and get benefited. Thank you all the participants for joining this particular session, and I thank all of them. Have a nice day. Thank you, sir.
Thank you.
Venkat sir, thank you, sir. Akila madam,
Oh,
thank
thank
you.
you.
Akila madam,
Thank
thank
you.
you, madam.
Thank you.
Thank you,
Mr.
sir.
Venkat.
Thank you.
Thank you, Mr. Venkat, for the wonderful